Oh, hi. Hi, can you guys hear me? Okay. Okay. Uh, uh, Hopefully everybody can, yeah, can hear my voice. Don't know if the connection is good because last week I did it at home. My internet connection at home was excellent. I don't know here in UNIMAS. I just did a quick speed test just now. Yeah, it's not that fast. So hopefully everybody can hear me loud and clear. If it's not that loud or not that clear, yeah, increase your volume. Good to see people are coming. Come on, everyone coming. We have attendance around 43 now. Okay. Yeah, we can wait some more. some more for more members to come. Okay, good. Crystal clear. Clear. Maybe your internet is connection is very good. 55 now. Okay. If anybody is having a problem scanning the QR code, please let me know. Around 61. Saya punya tak ada bunyi. Saya restart laptop sekejap. Okay, no problem. Afternoon. Thank you for asking. Already makan breakfast. But yeah, I'll take lunch after this. Okay, for manual attendance, maybe because you are on the phone or something, just to let you know that the one that we organized last week, I don't know, all the lecturers now are having problem to access to do manual attendance for for a class that is organized like this, all groups in one class, right? And then I cannot do. I still last time I checked, I still cannot do manual attendance. So that's why some of you still don't have your attendance checked for last week. So I'll check again after this whether we can already access for that one, for to do manual attendance. Okay, and as usual, if you have nothing to talk about, okay, nothing to talk about, maybe mute your mic. Thank you very much. You can still put your manual attendance over there, your matrix number and everything, because the chat will be saved. I will be able to check it back later on. But last week saya tak boleh buat. I couldn't do it because the system doesn't allow. Because I open, nothing appear on the screen, and then I close and open it again, still the same thing. And then I got confirmation from other lecturers they cannot do it too. Okay, they're also having problem. So the administrator of the system has been notified, and I think they're working on it. I will check it back. I will check it again after this. Okay. So it's been 10 minutes since the session started, and now we have around 77 participants, over 90 plus of you, right? So shall we wait some more? Let me see. Participants attendance is at 77 now. Participant is 87 minus me, so around 10 of you cannot check in now. It's okay. It's okay. Just put your name there. We'll put it. I will try to do the manual attendance later. Because preferably I would like to start the lecture straight away. Because as you can see from the previous video, the actual lecture started 40 minutes after the video started. that was that was a long introduction to the session. Okay, so attendance is around 81 now. Okay, and then participants we have 85. So for those coming late, don't worry, I will open the QR code later on again. It's not like they can hear me, right? Because they are late. So it's okay. Yeah, so let's just start with our lecture for today. So I will stop sharing stop sharing this one, the QR code, and let's see. Files. Wait, share a file. Wait as I open the lecture note. Sorry, this one thing. Okay. Okay, so can everybody see this? So everybody has access to the what do you call this one, the lecture note. Okay, good. Okay, nice. I didn't actually I didn't know, I didn't know how the slide will be shown to you. Because on my screen it's a bit different. So when the first time I watched the video and I say, oh, okay, the whole screen was occupied by the slide. So that was nice because I thought it was going to be small like what I was seeing on my own screen. So it's good that when we say share when you share a slide, then you can see the whole slide on your whole screen. That was good. Okay, so let's start for today. So again, let's renew. Assalamualaikum and a very good afternoon to everybody. So it's been a while since we have a class on Monday, right? Okay, so we had a lot of holiday on Monday. this semester. So but just by seeing at the list of attendance, ada 5 atau 6 kali saja lecture on Monday. And I was unfortunate enough, okay, to hit all those Mondays. QR code Hadijah. Sabar sabar nanti. We already started tahun depan. Nanti saya letak. Nanti saya ni share balik just to make sure you don't leave early. Okay? Just to make sure that you don't leave early and stay until the end of the of the class. Don't worry, I will not be taking a lot of our time today. Hopefully we can finish early because like I said last week we'll have a session with the NC or TNC after this. So yeah, let's see if we can finish this early. Lunch, huh? Uh, Yeah, it's not that I can see you. Okay, it's not that I'm scouting for videos for everybody looking what you're doing over there. You can have lunch while listening. Okay, to the lecture. Just make sure to you mute your mic so that we don't hear you munching your food. Okay, so let's start. This is a continuation from last week, and this time around there will be a lot more calculations compared to previously. Okay, so let's start. We're still on DC motors. Okay, still on DC motors. So yeah. Uh, so first we are going to look at this one, induced voltage. Okay, induced voltage for one conductor. Okay, if the motor is connected to one conductor, so induced voltage have the what do you call it mm, the equation of E IND here, where this IND is induced, okay, is equal to BLV, where B is the magnetic flux density in Tesla, okay, T Tesla, and then we have the L, the length of the conductor in meter, and then we have V, okay, the velocity of the conductor. The velocity of the conductor in meter per second. So the induced voltage depends on three factors here. The flux. Okay, I think we have seen this previously also, right? In last week, the flux in the machine means that, like I said, the bigger the magnet, the stronger the flux will be, and the stronger the force or induced voltage will be too. So yeah, the size of the magnet or the size of the motor itself matters. And then second is the speed. Okay, this one is rotational speed, omega, of the machine's rotor, and a constant depending on the construction of the machine. So this is just what I call the revision from last week. Here again, okay, I think this induced voltage, E induced is induced voltage that is equal to the product of flux inside the machine. Because the keyword here is product. Product, as you can see, the equation is only here only involves product B darab L darab V, means the bigger the flux density, the bigger the induced voltage. The longer the longer the length of the conductor, the bigger induced voltage, and also at the same time the higher the velocity of the conductor means the bigger induced voltage as well. So it is a product of the flux inside the machine and the speed of the rotation of the machine multiplied by a constant, representing the mechanical construction of the machine. So here, by looking at this figure, you can see that the total induced voltage of the loop on the loop E induced is given by EBA. EBA is here, this length here. Okay, E induced at B to A here, this length here. Okay, let me see. Sorry, you cannot see the cursor, right? Again, just to make sure, you cannot see the cursor, right? Can somebody? Yes, no cursor. Yeah. Okay, thank you. So I will scribble on the screen. Okay, so this besarnya. Okay, sorry. That one is too big. Let's mana ini kah? Oh, not the line, not line. This one, square, oval. Okay, okay, this one. So this EBA, this one here, is the induced voltage at this part, this length, EBA, this one. Okay, and then ECB, CB or CB is at here, this one. Okay, and so on lah. EDC is the one here, and plus EAD, the one ni dah lain. Okay, the one here. Okay, so of course EAD is a bit different because there is no straight line connecting A and D, so you need to follow the length lah, the length here. Okay, so that is what these are talking about. Okay, all this are the things that shown in the figure. Okay, so E induced here is equal to VBL, VBL, okay, is where and then plus 0, because for CB, because of the direction of the connection, the B and C, okay, the induced voltage is 0 over there, okay, 0, and then DC, VBL again, plus 0 again with A and D. Okay, between there we can 0. So the total induced voltage will be 2 VBL. Okay, I hope you can get that. Okay, so from this figure we get that the value of induced voltage will be 2 B L V. Okay, 2 BLV. Okay, so just the rearrange of the formula over there lah. Okay, moving on. So basic theory for the generation of electricity using a generator is the conversion. Okay, conversion from AC to DC. Okay, AC to DC, which is the work of the generator. So I think this one is also a very basic. I think, has Dr. David explained about this previously? Because I think this looks like a revision from previously. Okay, just so you know the concept. Yeah, good. So the concept is the conversion from AC to DC. So moving on, using this one. Okay, for motor we use the left hand. For motor with left hand, and for generation we use our right hand. Okay, the gesture are similar. Okay, like this one, I think you can see what I'm doing on the video. The direction, the gesture is similar. It's just that you can see that the difference in direction for current, where current flows, and how the motion will react. Okay, that one will be different. Okay, it's just terbalik lah. You know your right hand and left hand, right? Actually, the apa terbalik. Okay, so just remember, if you're talking about motors, then we will use the left hand. For generator, we use the right hand. Okay, right hand rule. So don't be confused for that. And then left hand rule, this one no need to explain further. And then right hand is if you just have a cable, you have a cable with the current flowing. Usually this is not that strong lah. Okay, this is the induced, what you call that, magnetic field. The magnetic field using the right hand rule here. So if the current is flowing to this direction, this direction, and then you will have the magnetic, okay, the magnetic field, okay, generated, okay, in this direction, okay, following your fingers, this direction, around, okay, the cable. So usually this is not that big sebenarnya. The right hand, this magnetic field, usually it's not that strong. Okay, usually it cannot be detected, but just so you know that it's there. Okay, it's there. And then again, this one basic theory for motoring tadi cuma just terbalik tadi compared to the generator, where the generator we use the right hand rule, and for the this one for the motor we use the left hand rule. Okay, not much to be said there. And this one also last week sama okay, this one also we have looked at this one before, right? Okay, here are the basic elements: the field circuit, the armature circuit, the commutator, and brushes. I think this one is we have seen the build. Okay, the build for the motor, so no need to explain this again. Okay, hopefully you can don't worry, this one is just a revisions. I will share this slide later for you guys to look at. So and then we have this classification of DC motor. So you know, right? We have separately excited DC motor, shunt DC motor, series DC motors, and then compound DC motor, PM permanent magnet DC motors. So DC motors are grouped according to how the excitation field is produced. Okay, how it gets the its current. Okay, how the motor gets its current will decide its type. Okay, so they are grouped according to how the excitation field is produced or how the field circuit is arranged. So each group exhibits a distinct speed torque characteristics, and each group is controlled by a different, what do you call that, different means. Okay, so by the end of this slide today, there will be a bit of calculation lah on this one, speed control, speed control, okay, of a motor. I will leave that for later, tapa. So here is a DC motor. Okay, DC motor equivalent circuit, equivalent circuit based on the field windings arrangement. Okay, where you can see that ini kita panggil equivalent circuit, right? So the different types of it, I think there's an animation for this one, but yeah, it's not shown here because if there's animation, this app cannot show the animation. So tapa, the animation will be included later on. So we'll look at the type of the motor one by one lah. Okay, starting from this one, separately excited DC motor. So for this one, two voltage sources are required. Okay, so the field circuit is a permanent magnet for small motor, like less than 100 watt. And then field is constant and cannot be adjusted because this one, the field is using a permanent magnet. But the magnet itself is fixed there in the construction. So yeah, that's why it cannot be adjusted. Okay, so the field will be constant all the way. Okay, so the field current is smaller. Okay, therefore the wire cross section of the field winding is also smaller. So the field current is given by this one, IF. Okay, this susah pakai ni. Jap pencil tool. This one, this IF here. Okay, I have this one. I think, yep, this one here. Okay, IF is given by VF over RF, where the field resistance is bigger than the armature resistance. Armature resistance is this one. Okay, very simple. What do you call that? Very simple formula. So armature in this armature current is much higher. Okay, means that IA is bigger than IF. So the armature current is given by this formula. IA is equal to VT, because they said for this one separately excited motor tadi dia perlu two different voltage sources, right? This is number one and this one is number two. Okay, here. So the armature current is given by IA. Okay, okay, IA equal to VT minus EA. Okay, this is armature voltage, okay, over RA. So the developed power, okay, PD, is represented by the multiplication of IA and EA. So power P equal to IV, right? So P equal to IV, the the original formula, P equal to I darab dengan V, right? Okay. So the power developed by this motor, okay, can be calculated as EA, which is the V part, okay, EA, the armature voltage here, times IA, armature current. And that can also be uh, verified by using this formula. TD means this is the torque, I think. Okay, the torque. And ni torque, macam mana tulis torque? Yep. Okay, here torque. Okay, just so that kalau cakap pakai motor tak boleh lupa pakai torque. Okay, kena torque. Okay, pencil to pencil. Okay, okay, torque, and this one is the speed. Okay, rotational speed. So back electromotive force EA is equal to the voltage source VT minus the voltage armature resistance. So mechanically it is also equal. Okay, it is also equal to the developed torque multiplied by its angular speed. This one. Okay, torque darab dengan angular speed. So that's how you get the power of a motor. Okay, because sometimes we just want the value. Okay, we just want the value of the power. Okay, without knowing berapa banyak armature, this one armature, the electromagnetic force EA and current inside. So you can still calculate the power of the motor uh, by using its speed RPM darab dengan dia punya torque. Okay, so both formulas can be used to find power. Okay, moving on. So the power, developed power in the motor is equal to the output power consumed by the mechanical load plus the rotational losses. If there is no rotational losses, so we are talking about inilah what you call the ideal motor, but which usually is not the case. There will always be these losses, not just rotational losses. There are other losses too, like frictional and windage and benda lain lah. Okay, so usually the power developed is usually bigger than the power consumed. Okay, by the mechanical load. Means power that you can actually get from the motor is usually less than the power that the motor is actually generating. Okay, so similarly, the developed torque is equal to the load torque plus the rotational torque. So ini tadi, it's like talking about power. Okay, usually the torque value that you get, the actual torque that you get from the motor itself, is less than the torque that you calculate. Usually because torque, okay, usually torque is used, okay, because I told you last week, right? Torque is the ability to move an object, okay, the ability to move an object. So in order for the torque to start moving something, okay, it has to go against other forces. Okay, that's where the losses come. Yeah, that's where the losses comes in this case. So usually the calculated value is usually higher than the one that you can get actually in real life. Okay, so the EA is calculated using this formula. The one inside tadi, yang inside dalam sini, this one, EA here, okay, is calculated using this formula. Is equal to K phi kan, phi omega. This one is must be in radian per second, radian per second, because kalau yang lagi satu tu RPM, yang RPM, this K will be this one. Okay, kejap saya padam. Because last week, if you remember, there are two formulas. Okay, two formulas for this one. So it's either kalau kita pakai K, if this one must be in radian per second. If this omega is in RPM, revolution per minute, then kita kena darab apa tu? Ni kan 60 semua kan? Okay, 60. So there will be apa nama, the formula will be a bit different lah. So you can refer to the lecture note from last week to see how this formula can be, what do you call that, transformed if you want to use RPM in the calculation here. Okay, so we substitute this EA into the power formula just now. Okay, the power formula which was this one. Okay, this formula we substitute that here. Okay, this EA. Okay, so in 2PD, we'll give the developed torque as TD equal to K phi IA. Okay, so we substitute IA. Okay, IA into TD. Okay, IA into TD means in this case apa ni? IA into TD. This one. This IA tadi mana dapat IA kat sebelah dia? Ada rumus IA ni. Sini. This one. Okay. This one. Okay, we bring this into TD, into here, into the, no, not that one, the new formula here. Here, this one here. We put it here. Okay. So you have a new, okay, torque. Okay, torque formula. Like this one. Okay. So K phi Vt minus K phi omega over Ra. Okay. So omega is either the speed current equation, or it can be divided into this one lah. Okay, speed torque equation or the speed current equation. Okay, both can be used. Okay, by this using this formula. Okay, don't worry too much about it. Kita maybe apa right now kind of bit confused, right? Mana nak pakai ni, bila nak pakai ni, how, what kind of situation that we are going to use this formula. So there will be what do you call that, examples in the end of this. So don't worry. So you will see in the kind of situation that these formulas will be used. Yeah, it's easy. It's easier to look at it from the using the example, right? Okay, so tapa. So that one really for later. Okay, so right now, uh, what we are looking here is the speed torque equation for omega tadi. Okay, so tadi omega can if we want to find omega for speed torque equation, omega will be equal to this one Vt. These are not new formulas, huh? These are not new formulas. They are just derived from this. Okay, this omega is just derived from this one. Okay, this one here. Yeah. Okay, this omega. Okay, so depends whether if you want to use it in the speed torque equation and speed current equation, this omega, okay, can be calculated. Depends on this one. Okay, for speed torque equation, because this one just now is straight up a torque equation, right? Torque and speed. Okay, torque and speed. There's no current in here. Okay, there's no value of current in here, so it's a straight up torque and speed equation. So you can just transform the formula. Okay, tukar into omega equal to Vt over K phi minus Ra TD over K phi ni darab ni kos dua. Ni darab kan. Okay. So yeah. But when we so the figure here, figure 5.4, the speed torque characteristic of DC separator motor is showing. Okay, is showing this. Okay, showing the relationship between speed and torque. Okay, so as you can see, as the speed increase, okay, as speed goes faster, as the motor spin faster, torque goes lower. Right? Okay. This one we have seen the formula. Okay, we have seen the formula last week. Yang speed dengan torque tu, kan? Okay, you can refer back to the lecture lecture from last week. That is the only way that they will work. Okay, the higher speed, the more speed you have, the lower torque. Okay, you will have. Okay, so it's to see. Okay, to actually see this phenomena, you can actually see it on your own. Okay, it's not that saya menggalakkan ya. Okay, it's just like kipas angin lah dekat rumah. Okay, if you are staying at home and then your mom asks you to clean the fan, so because usually the fan tu ada ada yang debu-debu tu kan. Okay, the dust around its blade and everything. Okay, don't touch the blade lah. Okay, when the fan is spinning, don't touch the blade. Okay, right now you take the spinning of the blade as the speed. Okay, this is just an example lah. Okay, you take the spinning of the blade as the as the speed, rotational speed. Okay, and then you use your hand. Okay, whatever lah. Okay, we use protection cover. Your hand. Okay, you you consider your hand as a load. Okay, so you want the fan to start spinning you, your hand. Okay, the load. Okay, so when the fan is spinning, you try to stop it. Okay, if you hold the center of the fan, okay, in the middle there, okay, it stops, right? If you hold it strongly with a nice grip, it will stop, right? Okay, because at high speed, it cannot sustain a high level of torque. Okay, so that's why it becomes slow. It becomes slower as it tries to, what do you call that? It tries to resist your hand holding it, right? You try to hold it and stop it, okay, from spinning, and then the speed of the fan become lower as it tries to resist, okay, your hand that is acting as the load from stopping it from moving. Okay, that is actually the relationship between stop speed and torque. At high speed, there is no way a motor can sustain a high load, a high torque. Okay, it just doesn't have it. Okay, it has a speed, but it doesn't have a torque. Okay, so in order to have a bigger torque, you have a to have a it usually it's generated at a lower speed. That's why using a figure 5.4 here, you can see the relationship. Okay, usually it's not this linear. Usually, if we uh, if we put in the losses and everything, usually it's not this linear. Eh? Usually dia macam ni sikit ke ataupun like this. Okay? Usually it's not linear. But this is just to show the relationship that as you increase the speed, the torque become lower. And then you can also use the formula just now. This again this formula to in the speed current equation. In the speed current equation, where first you need to replace the TD IA TD over KO, which is this part. Okay, you replace it into IA. Okay, you replace it into IA. So now you get yourself a speed current equation. Okay, where from a certain speed, you can get the value of current. Okay, from here, okay, from this equation, you can see that you can control the amount of speed, right? You can control the amount of speed. Okay, you can control the motor speed, okay, by varying the current. That is the basis. That is actually the basis of the basics for speed control, motor speed control, where you just varies this IA. Okay, so that the value of speed will differ. Okay, you can make the motor spins faster or slower by varying the amount of current. But usually we don't. Yeah, but usually we do it. We do this. We vary the amount of current by varying this one, right? Okay, resistance. Okay, if you put a itu selalu kita we varies the amount of resistance. So the higher the resistance, the lower the current. So the lower the motor will be, the slower the motor will be, and the lower the resistance, the higher the current will be. Because V equal to IR, right? Okay. So if a V is constant, so you lower the amount of resistance, so the current will increase, and thus the motor speed will also increase because the one go lower, this one go higher, and there's the only way this one to go up is up. So yeah, more current means more speed. Okay, so this is the basics for motor control lah. Okay, usually it's not that simple, but yeah, just so you know that this is how. Okay, simply said, how motor speed is control. Okay, moving on to the next one. So if the rotational losses, okay, the rotational losses, apa dia cakap tu, are ignored. Okay, means the motor is ideal. Okay, so the torque, okay, TD is equal to the load torque, the shaft torque. Okay, and the no load armature current can be assumed to be zero. Okay, if there is no losses, so the armature current is zero. So the no load speed can be obtained by setting the load torque or armature current equal to zero. Okay, if we are talking about an ideal motor, yeah, we just assume that the rotational losses is not there. Okay, so this will become zero. Okay, this will become zero, and then when this becomes zero, this part also become zero. Okay, this part becomes zero. So this whole part also become zero. So we have a new equation. No load speed for a motor can be obtained, okay, by using this formula. Okay, this new formula here, omega zero. This is they are denoted here as omega zero, which means this is a no load speed. Okay, no load speed. Okay, yeah. Okay, the no load speed omega zero equal to Vt over Kv. Okay. So in reality, the mass of the drive system and the rotational losses are the base load of the motor. In reality, so the no load speed is therefore slightly smaller. Slightly smaller, not bigger. Okay, because like I said, for ideal calculation, this will be the value, but in real life, it will always be smaller. And it depends on the amount, the size of your motor and the size of the, what do you call that? The size of the magnet that you are using. If the stronger the magnet, then yeah, the losses will be lower because it will have a higher torque, okay, to start moving the machine. Okay, and then the bigger your motor, the heavier the shaft will be, right? Okay, so when the shaft become heavier, so the resistance from gravity and all of that, okay, will also become bigger, and then friction will also become bigger. So yeah, the initial torque to initiate the movement will also be bigger. So you will have, in terms of speed, you will have a bit lower. Okay. Okay, so this one, siapa ni? Survey broadband, apa pasal? This one is, how many? 62 slides, this one. Yes, 62 slides. So this one is how many slides? I don't know. So, tak apa, don't worry. Okay. Yeah, it seems like, are you in a hurry to go somewhere, or you have any other class after this? Tak ada? Okay, just tell me if there's anything, Okay. So, moving on. Next one. Okay, okay. So in the steady state, okay, in the steady state means, how to say steady state? Steady state is, okay. So, jap. Sekarang dah masuk waktu Zuhur. Ada azan now. Where is the azan? I need to. Oh, which phone? Sorry, this one. Sorry, tak elok cakap waktu azan, so just stop the azan lah. Where is it? Okay, here. Okay, sorry for interruption. Okay, so in a steady state. Okay, so do you know what is a steady state? Dah belajar control belum? Belum ah. Okay, control system, apa tu? Control system engineering. CSE kan, control system engineering kan subjek dia. Kan itu tahun bila? Tahun 3. Third year. I think that one will be third year, right? Okay. So third year. At least know your curriculum. Come on. Apa kamu belum third year, then you just don't care what you will learn next lah. Yeah, then you will learn about control system later. Okay, control system engineering later. So steady state is something that you will see quite often, okay, in that subject, steady state. Okay, like just like the name suggests, just like the term suggests, steady. Saya orang Sarawak cakap steady, yeah, steady kan. Means, yeah, it doesn't move anymore. It doesn't fluctuate. Okay, it doesn't fluctuate. It doesn't, you know, go up and down anymore. Okay, in control, there is what they call a step. What they call as a step response. Okay, where, okay, the starting from zero. Okay, the this one kita letak as this one is a response lah. Okay, so we will have this at a certain amount of time. At this one kita letak sini lah. Okay, after dt ini masa. Okay, t. Okay, ini dia punya response lah. Ini response. Okay, just take this blue one as a signal. Okay, you increase the voltage from from state 0 to another new state. Means kalau sini kosong, sini satu kah contohnya. Right? Okay, ambil example like here is 0. Susah nak nulis ni sebab dia kacau masuk situ. Okay, here is 0 and then here is contohnya 1 lah contoh. Okay, okay. Okay, here is contoh 1. Okay, you increase the input. Okay, you increase input from 0 to 1 contohnya. And one after a certain amount of time lah. So your machine, okay, will react to this depending on a lot of what do you call that? A lot of alamak, apa ni cara nak ambil kacau. Usually they will react this way. Okay. Okay. Ini lurus lah. Tak macam tak lurus kan. Nampak saya lukis buruk. Tapi this one lurus lah. Okay, already stay. Lurus lah. Tak ada, this one tak ada berubah lah. Okay, this stay. Okay, but this one memang ada a bit of overshoot. This is what we call as an overshoot. Okay, it goes down a bit here. We call as undershoot. Okay, and then you will learn a lot about this in control system later on. The term steady state. Okay, the term steady state here is this state, the one that is already stable. Okay, the one that is already stable means it doesn't go overshoot and undershoot anymore. It goes like the input. Ni sepatutnya tadi saya letak warna merah tu ya. Okay, so jangan saya letak tukar. This one is the response sebenarnya. Okay, okay, this one is the response. Wait, susah lukis pakai ni. Maybe on your screen, I don't know how it looks, but yeah. Okay, the system will respond like this: up, down, up. Okay, 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 and then it follows the input. Okay, this is output. Blue is input. Ini sebenarnya kosong lah. Sini sepatutnya kosong, but I cannot draw this one following this because the system doesn't allow me to draw because the drag. Okay. So just assume both started from 0. Okay, both started from 0, and then suddenly the input is increased from 0 to 1 after certain time. This one t something lah, t lama t. Okay, after t this one is increased. The input is increased from 0 to 1 contohnya. Okay, so the system, your system will response, okay, to follow the input. Okay, the output will try to follow the input as it tries to follow it, depending on the transfer function. Okay, transfer function and the damping ratio of the system. Okay, sometimes the system will what do you call that? Will produce this kind of overshoot. This is an overshoot. Okay, overshoot. Okay, more than the one that the system, what do you call that? The input want it to be. So in order to correct that, it goes down. But usually when it tries to correct it quickly, so it goes under. Okay. For what do you call it? For a good system, usually this doesn't last long. Okay, only for a certain amount of time before it stabilize here, which in this case kita panggil as a steady state. Okay, this one this area, okay, this area that saya letak dalam purple ni, this one, okay, is not steady state. Okay, this is not steady state. The one that we call steady state is the area after this one. Okay, the one that is already not fluctuating. Okay, the one that is not fluctuating, the one that is showing the no more changes, okay, in output. Okay, that is what you call a steady state. Okay, means when we're talking about motor, okay, when you control the speed of the motor, sometimes, okay, you need it, okay, you increase the current. Okay, you increase the current, and then the motor become faster as a result, right? Later that you know, when you increase the current, you actually set the motor to spin at a certain RPM. Okay, you want it to spin at a certain RPM. But as the motor responds to your input, to your request, means you increase the current, right? It shows something like this. Okay, sometimes it spins faster than it should, but it corrected, and after several time, after a certain amount of time, now okay, it spins at the correct speed that you wanted. Okay, so that is at steady state. Okay, we are not going to talk about this one, overshoot, undershoot, yet, because this is something that you will learn later. Just want to show you what is this, the steady state. Okay, so that, just so you know. Okay, clear for steady state? Okay, because I don't want to move on talking about steady state while you don't know what is steady state. Boleh faham tak steady state? Ada yang masih ni? Ada yang blur, tak faham steady state? Okay, good. Yes, just so you know, this the steady state. Because in this purple area, the purple circle here that will show you, there's a lot more calculations there. Okay, will be involved there. The rising time, settling time, dia punya, there's a lot more there. So that's why I don't want to touch. I don't want to touch that yet. Okay, it's not for you yet. Kamu masih tak umur lagi. Okay. Melainkan siapa yang repeat lah. Ada yang repeat this one. Tak ada kan? All of you taking this for the first time? Ada yang repeat? Tak ada? Okay, kalau kamu tak repeat lagi, yes, ada. Okay, if you haven't repeat this yet, so yeah, kamu belum cukup umur to talk about the one in purple. Okay, the red line represents the output response. Okay, response means you have a system. Contoh, whatever system that you can think about. Big ones like macam macam apa? Macam aircon, macam lift contohnya. Okay? Macam lift ke, ya, lift dalam bangunan tu. Okay, lift, aircon, kipas angin, but in the case for this course, motor, a simple motor. Okay? That is what the red line represents, because usually response cannot give the output the same as the input. Okay? You flip the input like this, usually response will delay. Okay, in ideal situation, of course, you increase, the response goes straight with the same line as the input, right? But in practice, okay, usually response will have a delay. Okay, will have a delay, and this is what happened. Okay, the red line is what happened. It tried to match the input. Okay, it tried to match the input here by trying to go as quick as possible to the steady state. Okay, so depending on the transfer function, depending on the damping coefficient, okay, the damping ratio, okay, the amount of time a system, okay, the red line, to reach the steady state will differ. Okay, so we are focusing on the red line here. Okay, red line when it's already the same line, reaching the same line as the blue line, input and output are the same now. So that means that usually, if we talk about it more detail, then usually the red line selalunya dia tak sama. There will be a case of like this, the actual case. If we zoom in the green area, this is yang blue tu, anggap dia garis lurus lah. Sorry, ada method nak buat garis lurus. Ada method apa guys? So this one. Okay, this one. Okay, so contohnya warna biru. Okay, this is the input. Okay, the green area, input. So in most cases contohnya, okay, so ambil dulu red line, saya buat red line. Okay, if you really go and zoom there, usually it will be this kind of cases. Okay, it will not match the input to the dot. Okay, there will always be this, what do you call that, small gap. Okay, because of losses and all tadi yang kita cakap before this, right? Okay, output will always be smaller than the input. Okay, usually this is the case. There is always this small gap, very small gap between them. Okay, yes, the actual output, yes. Okay, the red one is the actual output. There will always be this gap, but once this state, okay, once this state is reached, okay, once this state is reached, this is what we call as the steady state. This one, okay, steady state. The value, although it doesn't really match, okay, doesn't really match the output to the dot. So satu memang on the same line, not like that, but it's actually more like this. Okay, atas bawah. Kenapa tangan saya nampak pelik dalam tu? Okay, it's actually more in the case of like this. Okay, but there is no more fluctuation, right? There is no more oscillation there. The value stays the same. There is a constant as the input suggest, as the input wanted. So this case is what we call as the steady state. Okay, faham? Okay, this one zoom. You just imagine saya zoom lah in this green area going to this green area. Okay, so that is steady state. So in the steady state means the motor already spinning at a constant RPM. Okay, the RPM of the motor doesn't change. Kejap dia pergi laju, kejap dia slow, kejap laju, kejap slow. Tak ada. We're talking about steady state means the rotation of the motor is actually already stable. So the developed torque is equal. Okay, is equal to the load torque Tm. Okay, because at a steady state now, the initial torque is no longer needed. Okay, when the motor is actually already spinning, okay, the losses becomes less and less. Okay, this case you can just imagine you trying to push a cart. Okay, you are trying to push a cart. Okay, when you start pushing a cart, okay, when you start pushing a cart, the cart is still not moving. You start to push it. Okay, you need a lot of force, right? You are the one imposing torque now. You want to push the cart. First, it will need a lot of energy, right? A lot of force, okay, to move the cart, right? Okay, and then compare that to the situation where the cart is already moving. Okay, the cart is already moving, and then you adjust, there to keep it moving. So the energy required for those two situations are different, right? So you will realize that the torque, or in this case the energy required to push the cart that is already moving is way less than when you want to start to push it, right? Okay, that is the that is how torque works. Okay, so when the things are already moving, means in the steady state here, means the motor is already spinning constantly at a constant speed. A higher amount of torque is not needed. So that's why, contoh tadi macam if you're talking about a car, contohnya. So that's why when you want the car to start moving, you start with gear 1, because gear 1 has lower speed but higher torque. But as the car moves, or when the car already moves, right? Car already moves, you want it to go faster. Okay, and then sometimes you want to sustain your car at a high speed. So you change gear. Okay, you change your gear to the higher speed, means gear second, third, fourth, and finally fifth, and then sampai the sports car, sixth gear, right? Okay, you change it to the higher gear, which has a higher speed, but with a lower torque. Okay, just to maintain the speed, the high speed. Okay, so that's why here, when at steady state, so when the losses are very low, no more initial torque needed, the motor is spinning just as it is. Okay, so the developed torque is equal to the load torque. Okay, we can just ignore the losses. Just you can just assume there's no more losses. Okay, so at a given value of load torque, speed of the motor drops by an amount of delta omega. Ini bukan W, this one is omega. Okay, delta omega, that is equal to the second, okay, term on the right side of the speed torque equation. So this one, the delta omega is equal to RA over K V dari square darab dengan TM, which is the load torque. Okay, ini tadi yang asal lah, ini yang this one, don't be confused, ini bukan rumus baru, this one is the one that on the previous. So the speed of the motor can then be expressed by using the no load speed and speed drop. Means now the actual, okay, the actual speed of the motor at bukan at steady state is now can be represented by tukar color pula. Okay, can be represented by using this new formula. Salah. This one. Okay, just by, okay, kita kiraan tadi of this one, the zero state tadi minus dengan delta W, which is this one. Okay, this is the speed at steady state. Okay, and it can be seen here, the delta W, which is this one, the delta W, what the delta W is actually this one. Okay, is actually, alamak. No, salah. Ini apa ni? This one, no, but alamak. What is this? I cannot delete this. Salah. Okay. Oh, ada laser pointer, this one. Oh, now you can see cursor. Can you see the cursor? Oh, okay. Yeah, now dia ada laser pointer lah pula. Okay. So this, okay, so this one, this omega W is actually this one. Okay, we're talking about, and this difference, the actual operating point of the motor, okay, this omega here, okay, can be calculated using this value, which is, if we see from represented by this one, by this figure, is somewhere around here. Okay, and remember, this is only at steady state, means you don't change the value of current anymore. Okay, yang current kamu tak tukar, resistance kamu tak tukar. Okay, no more. That one is not steady state. Okay, if you still changing, if you are still changing the amount of current, then we are talking about this one. Okay, you are talking about this one, because the motor will still, the speed will still fluctuate. Okay, but this is only for steady state. Okay, only for steady state. So the actual speed of the motor can be calculated by ini tadi at no load speed minus dengan this one, apa dia panggil, omega W. Okay, omega W, salah, delta omega. Okay, this one, the speed drop of the motor can be calculated using that formula, and then by setting the motor speed to 0, okay, the equation for the starting current and torque, okay, kita buat calculation this one. Okay, if this new formula, these formulas are ini, jangan pakai ini, kita pakai this one. Not this one, salah. Tak ingat, this one. Okay, this. Okay, kita we get it all from here. We get it all from there. So by setting the motor speed as 0 tadi, okay, if we set the omega as 0, then we will have the initial torque, okay, the starting torque, the torque that is required to start moving the motor as uh, this one is initial torque, TST equal to K Vt over Ra, and then the initial current, okay, initial current as Vt over Ra. And so these equations provide information on the starting behavior of the motor. Means you need this much torque, okay, for the motor to start moving. Less than this, okay, means you don't apply enough voltage, you don't induce enough voltage into the motor will not start moving. Okay, that is what this means. The motor tadi, you want it to spin, then you need to put a voltage, right? Means kalau the motor is the requirement is 250 volts, you put it lower voltage than that, you induce a lower voltage than that, then it cannot move. Okay, the motor will not start moving, not because the motor is faulty, but because the condition of the starting torque is not met. Okay, the same with current. The same with current. SRA is constant. Usually it is constant because this is built in. Armature resistance is built in the motor itself. So this one is constant. So this IST usually it depends on the amount of voltage you induce into the motor. So lower voltage, if the voltage does not met IST, so yeah, the motor will simply not moving. So there are two of them: initial current and initial torque. Okay, for the motor to start moving lah. So this equation provides motion and starting behavior of this motor. So since RA is small, okay, even though it's fixed, but it is small, the starting torque is large. Okay, when the source voltage is equal the rated value. Okay? So it is advantageous when the motor has to start under heavy loading condition. However, the high currents can cause damage to the motor windings. So here is where it is different, a motor and engine. Okay, we're talking about the engine in the car, yang internal combustion. So for internal combustion engine, it has zero torque, zero torque at zero speed. Okay, as motor on the other hand, okay, you just need to keep this in mind. A motor has its maximum torque at zero speed. Okay, so I don't know if you remember during the class session, I told you when you start to induce a voltage into a motor, it spins straight to a maximum speed, right? Okay, it has a maximum torque at zero speed. That is the difference. Okay, but always remember it is advantageous, but high currents can cause the damage to the motor windings. So inducing more currents doesn't always mean better operation. Okay, supply too much and it can destroy the motor. So excessive currents going to the winding means it will generate large losses. So and which large losses usually in machines, large losses is equal to heat. Selalunya, if you're talking about machines, motor, most losses in machines are in the form of heat. In the form of heat. So over time, this excessive heat, the heat will melt the winding insulation, and when things melt, it will cause short circuit. So that's how it will damage. Although it has its maximum torque, means although it has its maximum torque at what do you call that? It's zero speed. Doesn't mean that to make it work better, why not induce the high amount of current from the get go? Okay, it doesn't work that way. Okay, there is a limit of the amount of current that you can induce. Okay, so always be careful for that. Eh, apa ni? Kenapa balik sini? Okay, so the control of separately excited DC motor. Okay, so we're talking about the control. Okay, apa sahaja bagi kiri kanan ni? Ini animation kah? Oh, boleh scroll the kiri kanan. I don't know. Okay. Just remember tadi dia punya apa the basic tadi ya. The basic is what happened? Is this one? Okay. So to how to reduce the starting current? Okay, method one tadi is by this one lah. Okay, by reducing the voltage. So method one is to reduce the voltage. So an adjustable voltage source is employed. Means you don't just put your plug it into the wall and then switch on. Then you cannot control the amount of current and voltage going in, right? Okay, so you employ an adjustable voltage source. Okay, and then this is common method. Like I said today, the basics for motor control is to adjust the amount of current going through. So by varying, okay, using a variable voltage input, you can what I call that varies. You can control the speed of the motor. Okay, so that is the first method, the simplest method using the basics, okay, of motor control. Wait while I plug in my laptop. Ni tak the macam bateri dah nak habis. Break kejap. Aduh. Okay. Take 5. Pukul berapa dah sekarang? Pukul 1 lah. Saya jumpa ni tak lama lagi lah. Saya jumpa dengan NC dah. Sekejap lagi. So, yeah. So this is a common method tadi, and then when the armature voltage is reduced, okay, sorry, what is this? Okay, sorry for the interruption. Okay, so when armature voltage is reduced, the no load speed will also be reduced. Okay, because tadi formula dia berkaitan antara apa? Because they are related to each other, right? So by varying this will become the formula is still the same, yeah, but you can make sure that you can see that the value of the omega 0 become smaller, okay, because the V tadi is also now smaller, okay. Okay, and then for the same value, okay, for the same value of apa tu? Dia kacau situ tak tahu. Volt apa dia cakap situ? For the same value of apa? Voltage. Load apa tu cakap? Tak nampak dia kat situ. Okay, for the same value of the field flux tadi, the armature voltage does not affect, okay, the speed drop. Okay, the flux lah. Okay, so the slope of a speed torque characteristic is RA over KF square, which is independent of the armature voltage. Okay, so sebab dalam ni this value dalam this formula there is no voltage calculation, so it is independent from the voltage. So note that we are assuming that the field voltage is unchanged when the armature voltage varies. Hence, the characteristics are parallel lines. Okay, parallel lines here. So depending on the voltage depending on the voltage V1, V2, V3, if you differ the amount of voltage, you control the amount of voltage to a different value, so you will see the speed, the omega 0 differs, okay, depending on the voltage. So if the voltage keeps decreasing, it will come to the holding state where the motor speed is 0 at point 4. Here, this one. Motor speed becomes 0. Means, like I said tadi, yang in the formula before this, if you don't induce enough voltage, there is a starting current, right? Starting current means if you lower the voltage enough that the starting current is not met, so the motor will not spin. So this is exactly what happened here. So it come to the holding state where the motor speed is 0 at point 4. And at point 4 over there, omega 4, this one, omega 4 here is omega V4, the amount of voltage there, V4, sorry, apa salah saya potong sana. Okay, V4 um, over KB, or Kphi minus dengan RA, this is the formula tadi lah, untuk omega is equal to 0 here, okay, this one, this spot. So method number 2, okay, method number 2 on how to reduce starting current is by increasing the why is it moving like that? I don't know. This one just never happened before. So using this formula, okay, this formula here, to reduce the starting current, okay, we increase. Okay, if you don't want to change the voltage, you increase the amount of resistance, armature resistance. Okay, so if a resistance, there is an added resistance. Okay, you put a new value here. RA is not just RA, but RA plus an added resistance, means thermistor, apa tu yang variable resistor. Okay, you put it there. Okay, it's added to the armature circuit. The control operates at point 2. Okay, at point 2 where the motor speed is omega 2. Yeah, omega 2. Okay, point number 2 here, this one. Yeah, you don't change the voltage. That's why the starting is the same. The starting here is the same. This one. Notice that how this one is different compared to the one previously, because now the voltage is the same. Okay, the voltage is the same, so that's why this stays the same, because V is constant. Okay, constant there. Constant. Okay, V equal constant, so this is the graph that you will get. Okay, it starts at the same thing. So once you add, okay, this one, the first line is with just RA. Okay, the first line is just RA. The second line with added resistance. Okay, you add to the armature resistance by applying letak sana by setting up a what we call variable resistor there. Okay, so you will get a new operating point number 2. Okay, and as you add it up, you add up, so the operating point of the motor will be different. Okay, as you add up, but the starting point will stay the same because the voltage is constant. So so note that at point 2, okay, omega 2 is now, there's a slight changes, okay, slight change in the formula. So you now have a new formula, omega 0 minus delta omega 2. Okay? So this will change lah with omega 3. Here will be omega 3. Okay, and then here will be omega 4 lah, where omega 4 is basically 0, right? Omega 4 is basically 0 as you add so much resistance that the initial current, the starting current criteria is not met anymore, so the motor doesn't spin. Okay, so that is omega 4 here. Okay, or yeah. So note that the no load speed omega 0 is unchanged. Okay, omega 0 is unchanged, which is this point. Omega 0. Okay, doesn't change. Regardless of value of resistance of the mature circuit. And the second term of speed equation is the speed drop omega delta omega 2, which increases in magnitude when R at increases. So consequently, the motor speed is reduced. Okay, so two ways. Okay, based on this one, there are two ways using this IST tadi. Either you varies the amount of voltage or you varies the amount of resistance. Okay. So if the added resistance keep increasing, the motor speed decreases until the system operates at point 4, where the speed of the motor is 0. Okay. So the operation of the drive system at point 4 is known as holding. Okay. Holding means the terms is holding lah, but what it says is the motor doesn't move. That's it. Okay. So in this case, R at 3 is given as this point, this one. Okay, R at 3 is given as K VT minus TD minus R. Okay. So keep in mind that operating a DC motor for a period of time in resistance inserted in the armature resistance is very inefficient. Okay, this is very inefficient because the use of resistance is acceptable only when the heat produced by resistance is utilized as a byproduct or when the resistance is used for a very short of time. So actually the second method is not very recommended. Okay, the best method is the first one. Okay, for a temporary measure, yes, the second method can be used by you induce an extra resistance, but remember as you increase resistance, using by this formula, KP equal to I, aduh, kacau lah datang ni. Okay, I square R. Okay, as you increase resistance, okay, this one. Jap. Tu apa tu? NC dah all apa tu? Classic load talk, offload talk. Apa ni? Kamu buat talk ni apa pasal? TikTok? No. Oh, okay. So this one, why the second method is not recommended because of this. Unless it's for a short time, unless it's just for just something that you need to do, okay, for the system to require this. Unless if that's the case, we don't recommend the second method because based on this formula, P equal to I square R. You know this one, this formula, right? Apa ni? Formula apa ni? Can somebody put it there? Dekat chat. What formula is this? What power? Power losses. Yes, good. Power loss. Okay. Unless, because of this resistance. Once you increase the resistance, you increase the resistance means you are also increasing the loss. Means you're increasing the normal form of losses in machines, like I told you just now, it's in the form of heat. Means the higher resistance you induce to the system means you are inducing more losses. Okay, so that's why it's not recommended. Okay, so power loss, remember. But voltage is not here. See, P equal to I square R, just I and R. Voltage is not here, so that's why you varies the amount of voltage. It doesn't change in terms of losses. Okay, it doesn't affect that much in terms of losses. Okay, remember that. So the same method to reduce the starting current tadi. Okay, so hence the speed of the motor can be controlled by using two lah. Okay, adding armature resistance or varying the terminal voltage. The third one is the current is constant in this case, sir? No. the point of this is to change the amount of current. Okay, the point of speed control here, why we want to change to control the speed is because of this. The current is not constant. Okay, if you increase the amount of voltage, the current will also increase, right? If you decrease it, then the amount of current will decrease. Okay, so in a normal motor, armature resistance is small and fixed. But by adding R added tadi kan? R added. R added tadi. So by increasing this value, you are also decreasing the amount of current. So no, the current is not constant. The point of speed control is to this current, okay, to change the amount of to reduce the amount of current. So it's not constant. We want to reduce the current. So that's why tadi the first method tadi to reduce the voltage. Second method is to increase the resistance. Okay. So yeah, no, the current is not constant. Okay. The point of this is to reduce the current. Okay. So and then the motor goes into the holding state. Holding state if the current is no longer met. Okay, the starting current condition is no longer met. Means the speed of the motor, the torque, starting torque is also not met, so the motor become zero speed. Okay, zero speed means the motor doesn't move. Okay, so by reducing it enough, reducing the voltage enough, or increasing the resistance enough, you can decrease the amount of current to below the starting currents, thus stopping the motor altogether. It's just that okay, the first method is usually recommended. The second one is not so much. Another method is by adjusting the field flux. Right? This is harder to do. Okay, because usually tadi kalau if you're talking about permanent magnet, okay, permanent magnet moving coil tadi, permanent magnet motor, the magnet is fixed, right? The magnet is fixed there already, cannot change. So usually the flux stays the same. Okay. Apparently, you can still change. Okay, you can control the motor speed by changing the flux. Okay, so by changing the flux means that the strength of the magnet. Okay, you you manipulate. Okay, the strength of the magnet. But this only applicable for small motor only, because you can imagine a big motor, a big magnet. How do you want to change the magnet, the flux of the magnet so much? Because it's too big, right? So this only applies for smaller motor. Okay, smaller ones. Okay, so if the field circuit is permanent magnet, so inside the flux of the field is constant and cannot be adjusted. Okay, for small motor tak boleh ni. This one. It says here for small motor because the magnet is fixed. Okay. Not just for small lah. In this case of the permanent magnet, this one cannot be used. Okay. For other cases, okay, method 3. Okay, the method 3 for is adjustable voltage source is connecting the field winding. Now we are talking about the one outside the motor. Okay, the one outside, yeah. Because tadi separately excited needs two voltage source, right? Two voltage sources, the one inside, one outside. Okay, so now tadi up to the method 1 and method 2 tadi we were talking about the one inside the motor. Now we are talking about outside. Okay, so you by adjusting the voltage source connected to the field winding, so you reduce the field voltage and the field current. Consequently, the flux are also reduced here. Now we are no longer talking about the one inside. Wait, no longer talking the one inside here. We are talking the one outside. This one. Yeah, the one that is connected to the field. Okay, field resistance. Okay, so when you reduce the motor, the voltage here, reduce it here, so this one will also goes down, and thus uh, producing a smaller flux. Okay, smaller flux. Then when the field flux is reduced, so no load speed is increased in inverse proportion. Okay, in inverse proportion to the flux, and the speed drop delta omega is also increased. I think this one terbalik sepatutnya reduce as the VF reduce, right? This one is okay. So the sini increase. So the characteristic shows that because of the change in speed drops, the lines are not parallel. Okay, because it's not proportional. So with the reduce of V tadi, as we reduce the amount, okay, dia tadi dia ni apa nama? Betul lah, betul. Dia inverse proportional means the lower the this one, the field voltage, the higher the speed become. Okay, the higher the speed become. Okay, so instead of omega 1 it goes down, it goes faster. Okay. Okay, the things goes faster as the field current becomes lower. Becomes lower. So there's this example. Okay, kita ada satu, and then ada solution bawah tu. Satu, saya rasa berapa solution? Satu, dua, tiga. Okay, so I will not touch about shunt motor for today. That one we will leave it for later. So saya share dulu this one lah. Okay, I will share the whole slide, everything dulu. Okay, to the ELIP after this. Okay, so just look at this one on cases where we can use all the formulas yang kita pakai tadi lah. Okay, because tadi just remember with what we talked before up to this point was about a separately excited motor. Okay, shunt motor will be a bit different. Okay, that is the one that we will see after this lah. Okay, shunt motor, obviously it will have everything inside. Okay, see, everything is inside connected on one side. So the formula will be a bit different, but the concept is still the same. The concept is still the same, just the formula a bit different. So I will share this online. I'm sorry to I'm sorry to end the session early because I have a important meeting after this. So shall we see each other again on Thursday? Boleh? Okay, yeah. So pada siapa yang tak sempat tadi, mana saya ni? Okay, so I will stop sharing this and no, okay, I will stop sharing this, and for those yang nama perlu letak tu, yang nama apa manual attendance saya letak ni lah, Microsoft Edge tadi. I'll share again our attendance QR code. Masih perlukah QR code? Okay, so thank you for your attendance. So see you guys. So yeah, please have a try at the attention. Have a try at the attendance. Apa hal kamu pergi try attendance pula? Kamu pergi try example tadi lah. Pergi try example tadi. So yeah, familiarize yourself with the formulas. Jap, siapa yang nak pergi annotate tadi? Saya kah? No. Okay, so thank you very much for your attendance and see you guys again on try. Oh no, on try on Thursday. Okay, so siapa ni? Terapan sign in. Naim Sazwan. Betul lah, Naim Sazwan terapan lah. Okay, so just put your name there. I will try to again using the manual attendance. Hopefully they already fixed the system. so that we can access. Oh, by looking at the attendance going down 68, 67, itu kan berkurangan, berkurangan orang dalam bilik kita ni. Dalam kelas. Usually I'm the one who goes out first, right? And then yeah, now I have to stay until the last one of you log out. Dang it. Okay, nice. Oh, 58, 57, 54. Yeah, welcome. 53, 52. Now I'm doing countdown. And as always, I will upload the session on YouTube, and also share the link on ELIP lah. So yeah, if you think you want to catch up, yeah. Ah, thank you very much. You're welcome. 40 minutes. Ah, apa tak? Saya dah nang 2:45. Oh, saya dah mana aku dua dengan 25.